All right, so we're going to be able to, this expression here, we're going to be able to simplify. All right, so we're going to ask the question then, here, we're assuming that we're going to say, all right, let's just say the first step is fast and the second step is slow. And we're going to see whether that gives us an answer that's consistent with the experimentally determined rate law. So here, if we say this is fast and this is slow, basically what we're asking the question, is the decomposition of the intermediate or its consumption faster? So as we wrote this, then, we're saying decomposition is fast. The first step is fast and reversible, so the decomposition is fast. The second step is slow. The consumption of that intermediate is slow. So that allows us to change our rate. So what we're then saying in terms of, here's the words, here's sort of the equations, we're saying that this term here, this k minus 1 times the intermediate term, is a lot bigger because this is faster than this. This is slow. The rate of consumption is slow. So k minus 1 is going to be a bigger number than k2 times O2. So if we say that, if we say this is fast, that's a big number, this is a fast step, k2 is a small number, it's slow. If this is a lot smaller than k minus 1, and these are both appearing in the bottom of the equation here, that allows you to get rid of this term. So if you have something really big and something pretty small on the bottom of this equation, the really small thing is kind of insignificant. And so we can get rid of that here. So we can get rid of this term. So that allows us to simplify this expression. Now we have k1 times NO squared over k minus 1. We can also rearrange that and bring our concentration terms on one side. So we have our intermediate over our NO squared, and have that now is going to be equal to k1 over k minus 1. What is little rate constant k1 over rate constant k minus 1? What? Big K, right. So that's another way of saying the equilibrium expression. So it's the equilibrium constant for the first step is equal to k1 over k minus 1. So basically what we're saying then, if we have the first step being fast and reversible and the second step being slow, we're saying that the first step is really in equilibrium. So what allows us to say that? Well, if you have a fast reversible step followed by a slow step, that means that not much of your intermediate is being siphoned off by the second step, allowing you to reach equilibrium. So you can think about that in terms of this plot here. If you have reactants going to intermediate, and this is fast and reversible, so they're going back and forth, fast, reversible, and then very, very little of that intermediate is getting siphoned off. This is very slow. So very, very little of this is being siphoned off to products. So that allows that first step to really reach equilibrium conditions, because this doesn't really factor in, and so you reach an equilibrium here. And that allows you to simplify your expressions. So now we can go back with our simplified expression, and we can express it as rate constant k1 over rate constant k minus 1 times NO squared, or we can write it as the equilibrium constant 1 times NO squared. And we can plug that in, solving for our intermediate. And so if we put that now back into this expression, we have the 2 K1, K2. We have our oxygen concentration and our NO squared over K minus 1. Or we can have equilibrium constant 1 with our K2 and our 2. And now now we're consistent if we realize that the K observed that was given in the experimental rate law is a combination of all of our K terms. So it's a combination. You can't, at least in this experiment, you weren't able to come up with the individual rate constants. They just came up with an overall observed rate. And so that's all of our terms in there. And so if we put that in here, we realize that this is consistent with the experiment. And in doing these problems, it's OK to leave your little rate constants. It's OK to use equilibrium constants in there. You should show all of your work so that if you have a K-obs in your final answer, we can look back and see what that was equal to. So it's hard not to show all your work as you're writing through all of these on a test. But you can end your answer. It would be correct to end your answer here or here or here. So I don't care which K is in your final answer.